we're going to shift gears and introduce Tim Claridge. Tim Claridge hails from Oxford University, and he's going to be talking about NMR supersequences for efficient structure verification. So I'll pass the torch from Isabel on to Tim. And Tim, if you would, please take it away.
Okay, thanks, Darcy. Can you see my screen okay?
You bet.
Okay, excellent. Right. So I'd like to start by thanking the organisers for the meeting today, of course, and the invitation to speak, and to say really it's a very great pleasure to be able to present in honour of Bill at this special symposium today. So what I want to talk about today really is an overview of what we refer to as NMR supersequences, so methods that have been developed for efficient structure verification of small molecules. So of course, Bill's background is more related to natural products, and that's what he's best known for. My world tends to be more associated with supporting synthetic chemistry programs. So if we look at what we might consider to be the synthetic chemistry life cycle, if you will, where you have a chemist working away at a bench or fume hood for some time, producing novel materials which they would wish to characterize. And the typical protocol, of course, would be to select a series of 1D and 2D NMR experiments with a scattering of mass spec and a splash of infrared, perhaps, and then spend time considering these data sets and hopefully on reflection to propose a structure and verify whether that matches with what they were aiming to make or not. And either way, that information is fed back into the synthetic life cycle to go on to produce further materials, looking towards final products and so on. So in a big synthetic laboratory, the situation tends to be any chemist will have multiple samples they wish to characterize, and often they have these samples at multi-milligram quantities, so fairly significant amounts even by NMR standards nowadays. But also it means we have many chemists to support. So the lab I work in typically supports in excess of over 300 synthetic chemists. And what we're looking to do therefore is to try and optimize the use of our expensive NMR instruments to get data turnaround as quickly and as efficiently as possible. And this is where the NMR supersequences come in. So you'll also appreciate that structure characterization protocols nowadays rely essentially on a core set of core two-dimensional methods for routine characterizations. These will be homonuclear correlation techniques such as COSY and TOXY, HSQC and HMBC heteronuclear correlations, fuse-based correlations based on NOSY and ROSY, typically involving carbon, of course. But then, as we've seen already today, there's often requirements for other nuclei, perhaps nitrogen-15 and others one can imagine easily. And the typical protocol for collecting these data sets would be to sequentially acquire individual, or what are referred to as standalone experiments, and we collect as many of these as deemed necessary for the characterization of the molecules of interest. So the question then becomes, can we do this process any faster? And of course, there are a number of approaches that already exist to help in this. So one might be maybe considered a brute force approach, so we can use high sensitivity instrumentation to reduce the number of transients we need to acquire in our data collection to give us good enough signal to noise. So say cryogenic probes can contribute in this area quite clearly, and we've heard about those today as well. Sparse sampling methods, so such as non-uniform sampling, can help reduce the amount of data we need to acquire to build up our 2D data sets. So we collect a subset of our total data points required to build up our 2D experiment, and we reconstruct the missing points. This is something Frank will talk about later, and I'll come back to this just briefly at the end of this talk as well. But that's one time-saving device. Modern instruments nowadays tend to be built with multiple receivers, and these will allow parallel detection techniques to be used, so whereby we can acquire the NMR response from multiple nuclei simultaneously, and this has potential to provide for quicker data collection. These methods tend to be most useful, I would argue, when the sensitivity of the nuclear species are broadly comparable. And again, this is something I'll come back to briefly towards the end of the talk. Perhaps the ultimate example of fast data collection is the ultra-fast single scan methods, whereby we use spatial encoding. This is taken from MRI type methodology, where each slice in our sample correlates with a data point in our two-dimensional experiment. and these can allow data acquisition in just a single scan, as the name suggests. These are not widely used, I would say, currently, and I'm not going to come back to this in this talk today. So by way of introducing the NMR supersequences, then if we consider the common techniques we wish to use for routine structure characterization, we can represent the pulse sequences of all these experiments using this sort of cartoon representation I show here. So they all have in common a recovery delay where our proton relaxation, which is specifically important, the proton magnetization for these experiments. This is a delay in which it's allowed to relax after the previous excitation, so we can sample that magnetization again in subsequent pulse sequences, experiments. We have our experiment itself, which contains a series of pulses and delays. And then we have our actual data recording the free induction decay. And we cycle back round according to the number of transients we need to collect and the number of increments we need to define our two-dimensional data set. And of course, all these 2D experiments follow the same sort of cartoon representation. They all have their acquisition period where we collect our proton NMR signal. They have a recovery delay where we allow our protons to relax. And then they differ in their pulse sequence details in these colored boxes according to the nature of the spin-spin interactions we're trying to probe for each of these experiments. So if we were to redraw these pulse sequence elements in a more meaningful time frame, they would actually look a bit more like this. And what we see in each case here for all of these experiments is that the major time taken for all of these, for each acquisition, for each transient, is dictated by this recovery delay, this relaxation delay. And this is for a modest 1 second delay. Typical values would be 1 or 2 seconds for small molecules. So this represents a large part of time when our NMR spectrometer is dormant. It's just waiting for our proton relaxation to occur, and obviously burns a lot of instrument time. So the idea with the supersequences is to try and nest these experiments in such a way that avoids collecting these as a sequence of individual standalone experiments, and nest them in such a way that we use only a single recovery delay where we let all our proton magnetization relax, recover, so we can use that again. And then we collect our individual experiments in a single sequence in just one total experiment, and whereby these are now modules within our NMR supersequence. Now, for this process to work, then what we need to realize is that what each of these individual modules is doing effectively is sampling just a subset of the total proton magnetization pool that will be available in any NMR sample. So for example, the HMBC experiment that will detect long-range proton-carbon coupling interactions will sample just 1% of our magnetization, but it's dictated by the isotopomers that are present in our NMR samples. The HSQC similarly will sample just 1% of our proton magnetization pool. So in effect, we can consider a molecule with a carbon-13 such as this to distinguish between the yellow protons and the green protons. We sample these separately in each of these modules. Now, these subsequent modules here are based on the bulk magnetization, so that the protons that are bound to carbon-12 in our molecules, and these will represent around 99% of the proton magnetization available. And they are represented by these orange balls in this cartoon picture. Now, we could include, for example, nitrogen-15. So at natural abundance, that would mean we'll be sampling proton magnetization of about 0.4% of our total proton pool in a nitrogen-15 based module. So Alex Kupcha and myself published some work on this a few years ago, presenting these ideas for small molecule structure characterization, and we referred to this approach as NOAA, NMR by ordered acquisition using proton detection. And we can imagine combining very many different types of two-dimensional experiments as specifically tailored modules into these sequences, where we collect these in a particular order. We arrange these in particular orders to work. And in this particular example, this would be what we refer to as a NOAA 4 experiment. It has 4 modules, and we use these single letter codes to distinguish each of these. So a B, an S, a C, and an N. And what we have to remember with all of these and the design of these is that the output of any one module here effectively becomes the input to the next module, and so on down the chain. So these have to be ordered in a specific way, and these modules designed in a specific way for that whole process to work. I'm not going to go into any details of that today, but we can think of this as being like a domino type approach to data acquisition. We start our experiment and the output from one is fed into the other in a sequential way, much like the operation of a series of dominoes toppling over. When we get to the end, we wait a while and allow our dominoes to stand back up again, and then we kick them down again and repeat the process and so on. And of course, the time savings by this approach comes from the fact that now we only need a single recovery delay where all our proton magnetization is allowed to recover, followed by multiple acquisitions afterwards. And our time savings come from that approach. So how does this work in practice then? What's the workflow if we wish to use this sort of approach? Well, the NOAA sequence itself will operate as a single experiment, lead to a single compiled data set. And then we have scripts that will automatically split these data sets out into their constituent experiments. At this point, it will apply the appropriate processing parameters for the individual types of experiments, carry out all the necessary transforms, and give rise to a set of what one might consider to be conventional 2D experiments at the very end. So how does this actually look in practice? Well, here's an example NOAA experiment. This is actually a NOAA 4 experiment. It's a triple resonance example, so proton, carbon, and nitrogen here. So this starts with a nitrogen HMQC, has a carbon HSQC, and then a nested cozy and nosy combination at the end here. I'm not going to talk about any details of the pulse sequence here. I'll just point out that we have this D1 period at the beginning. This is our recovery delay for the relaxation, and our sequence. And as the first module finishes, the second module starts immediately afterwards, and the same towards the end for our third and our fourth modules throughout. And the result of this would be, as we would hope, conventional 2D data sets at the end. So we have a nitrogen HMQC, a multiplicity edited HSQC specifically here, our cozy experiment and our nosy experiment. And this is on a decapeptide as an example. And the key comparison here is that by collecting these data with this sort of NOAA type approach, we can get this information in 8 minutes on this sample. Whereas if we were to collect these 4 independent experiments with the same resolution, that would have taken 27 minutes. So we have this almost factor of 3 time saving by this approach. And one, of course, can imagine combining very many different modules, experiments together in this NOAA type approach. To NOAA 2, 3, 4, and so far we've gone up to NOAA 5 modules. And there are many hundreds of these, in fact, some more useful than others, undoubtedly, but there are many, many possibilities. And of course, the more of these modules we can string together, we can nest together in this way, the greater the time benefits that we have. So we can see that illustrated here. If we take, for example, an HMB as a standalone experiment, and then we build into this with appropriate module modifications, a NOAA 2 to a NOAA 3 to a NOAA 4, we can compare the time requirements for the NOAA experiments shown in blue here versus the combined standard experiments shown in red. We see some quite significant time savings. That's perhaps best represented on the graph over here. So we can see as we add the standard experiments and collect more of those as individuals, we see a significant increase in the time requirements for that process. Whereas in blue, the NOAA approach gives a much more modest increase in the time that we need. And of course, the reason for that is because a big hit comes in here, the initial time, which is where we have our single recovery delay in this approach. So here's an example of what might be a very common requirement for small molecule, for routine small molecule characterizations. This is a NOAA 3 experiment producing the HMBC, HSQC, and cozy combinations. And this was a test of the output and quality of the NOAA data, whereby we took the data, fed this into a computer-assisted structural elucidation protocol, a case regime, to see whether it could handle the data and produce significant and correct results. So the cozy, HSQC, and HMBC data were fed into this case program, and the top rank structure that came out was the correct one for gibberellic acid. So it suggests that the data that came out is sufficiently robust to use in these automated structural elucidation routines as well. Now, if we consider a sequence such as this, actually, I'll just note that again, we have these significant time savings, 20 minutes for the NOAA acquisition versus 45 minutes for the standalone experiments. But if we go back to this NOAA 3 sequence, we can consider that this last module here just samples the bulk magnetization that we have in our sample, and we can switch this for a whole range of different module X, if you like, which sample homonuclear magnetization. So we can have different flavors of COSY in the end here, a double quantum filtered COSY, a clean in phase, the clip COSY experiment. We can have TOXY modules, we can replace with NOSY, ROSY, or even the pseudo pure shift type experiments can be included on the end here as well. And in some combinations, we can put multiple homonuclear modules at the end here that we'll see a little bit later. So we have quite a lot of flexibility on what we can put together with this approach. So here's just some data sets exemplifying that. So these are all from these BSX type experiments, and this is just showing the X part of the data sets where we collect different homonuclear modules. So we have a double quantum filtered example, we have a clip COSY example here, we have a TOXY, for example, and a ROSY on this diterpene sample. And in each of these cases, we have, again, significant time savings of around about 20 minutes versus about 45 minutes for the separate independent data collection. So in some of the more recent work we've been doing, we've been looking at more detail in increasing some versatility and sensitivity in some of these modules. And in particular, we've been focusing in on the HSQC modules. This is often, of course, the core of many structure verification, structure characterization procedures. So we've incorporated modules that allow the use of sensitivity enhanced HSQC experiments and also HSQC TOXY experiments into one NOAA acquisition, and methods for combining these into one experiment as well. So in this scheme, we have what we refer to as a NOAA 5B, HMBC ST for the HSQC TOXY, S+ for the sensitivity enhanced version of HSQC, and COSY and NOSY spliced on the end. If we look at the data sets that we get out from this type of acquisition, then again, they look like the sort of 2D experiments we'd hope to see for structure characterization. So the HMBC, HSQC TOXY, multiplicity edited HSQC, sensitivity enhanced version, again, the COSY and the phase sensitive NOSY acquisition here. So this provides a fairly comprehensive suite of experiments that might be appropriate for small molecule characterization. And again, if we look at the time comparisons, and the NOAA experiment here took 23 minutes to collect all these data sets. The standalone versions with the same resolution would be 77 minutes here. So again, more modules, greater sensitivity, time savings. Now, I mentioned at the beginning other routes for time saving in our routine experiments, and NUS, non-uniform sampling, was one of those. So can we combine NOAA and NUS together? Well, yes, we can in certainly most cases. So here's just some examples from a NOAA 2 sequence to illustrate this. This is HSQC and COSY combined. And we're going to look at the HSQC data in particular. So here's a small molecule HSQC data set from this NOAA experiment, and the total took 11 minutes to acquire without NUS, so standard sampling of our 2D data here. And we can now incorporate NUS fairly straightforwardly into our sequences. It's encoded in the POS programs as we write them now as a flag to trigger NUS sampling. And we can incorporate 50% NUS and half our time, gone down to 25%, so a quarter of the time here, and this is going down as far as 12% in this case. For a small molecule, the data is still perfectly usable, and the whole 2D acquisition was just 1.5 minutes here. Now, alternatively, we can use NUS to not save time, but increase resolution, particularly in our heteronuclear dimension, so the carbon dimension here, for example. So in this case, we've actually used NUS sampling to keep the time the same, but sampled at 50%, which allowed us to double the data size in our carbon dimension, to double the resolution in this dimension effectively. And you can see the difference comparing this one with this one here. And here's just another example to illustrate that. This is now with a a NOAA3 sequence, so an HMBC, an HSQC, and a CLIP COSY experiment, a clean in phase COSY. This is showing the HSQC and the HMBC data sets. Without NUS, a standard sampling in our carbon dimension, and with NUS sampling in our carbon dimensions. And this is now sampled at 25%, but using that to give us a 4-fold increase in resolution rather than a time saving. So these are all 18-minute acquisitions for the 3 experiments. And we can see an improvement in resolution in the HSQC and the HMBC. And if we look at some of the projections along the carbon dimensions, it's perhaps a little easier to see. So the bottom traces are for the conventionally sampled experiments, the upper traces for the NUS sampled, and we can see, for example, here the better resolution from incorporation of the NUS sampling. So NUS is feasible. I also mentioned the possibility of using multiple receiver type experiments for parallel acquisition. So I'll finish here with an example of incorporating parallel acquisition into NOAA sequences as well. So this is formally a NOAA4 experiment, and we're going to incorporate proton and phosphorus detection in this sequence. So this is a BSC to start with. So it's the HMBC module, followed by a carbon HSQC, followed by our COSY module. And at the end, we have this, what we might call a C-squared module. So it's a parallel acquisition sequence. And in this, we start at this point using phosphorus magnetization, which so far has been dormant in our experiment. So we excite phosphorus, and that now becomes our source midway through this supersequence. And that allows us to do a phosphorus COSY experiment with phosphorus detection, but also in parallel, a phosphorus proton correlation experiment detected at the same time. So this gives us, in fact, 2 additional experiments based on phosphorus from this scheme. So we end up, in fact, with 5 data sets from this NOAA4, our COSY, our HMBC, and our HSQC. And then in addition, we have a phosphorus COSY and a phosphorus proton heteronuclear COSY experiment. And for example, in the ATP molecule used here, this allows us to characterize our phosphorus phosphate side chain and connect that to the sugar in ATP here. So there are options also for incorporating multi-receive type approaches into the NOAA family also. So just in conclusion then, I'll finish by saying that these supersequences provide a rapid route to data collection by the fact that they need just a single relaxation delay for all our proton magnetization. Then we record our selected modules in this domino type approach, which lead to this significant time savings. It's a scalable approach. You can build modules together in certain sequences, and so far we've gone up to 5 acquisition modules in total. In part, that's limited by the pulse programming on the spectrometers, in fact. It's modular. There's a plug and play element to this. You can choose the modules you want and then string them together. And this has been exploited by my student, John Young, who's been working on some of these sequences, and he's developed this website now where you can select the modules that you wish included, hit the go button, and it will produce a pulse program that is ready to go according to the NOAA sequences that you wish to use. And these sequences are robust. A lot of the design work in building these goes into tailoring the modules themselves from conventional ones to try and reduce artifacts and, of course, retain the magnetization at each stage for the subsequent modules. And finally, a lot of these are available. So some of these are already in the Topspin Pulse Program library, and we have many more sort of suggested by this modular approach here that we'd be happy to make available for people to use if they wish. So just finally, some acknowledgements. In particular, I'll highlight John Young, who's a graduate student working with me now and developing a broader range of these NMR Supersequences. And of course, this has been a collaboration for a few years now with Eric Kupcha at Brooker on the development of the whole suite of the NOAA experiments. And I include finally a couple of photos of Oxford. This is our lab where we are, and this is one of the old buildings in Oxford. particularly for the benefit, and Rob and who are former graduates of Oxford. So I'd like to finish by thanking you for your attention and saying a big congratulations to Bill for his special day today. Thanks very much.